Hello everyone, my name is Yunjing. I'm from the University of Michigan. In this talk, I'm going to present to you Bobtail, avoiding long tails in the cloud. So today, public cloud services are used everywhere. Many applications we use every day rely heavily on those services, like especially Amazon's EC2. As a result, they have enormous impact on the consumer internet. For example, as of April 2012, a third of all internet users will access websites built in Amazon's cloud at least once a day. However, building those large applications in the cloud is very challenging because usually those user-facing applications have a very tight deadline on end-to-end response time. For example, 300 milliseconds is not uncommon. Meanwhile, as the scale of your application gets larger, you get more moving parts. For example, it has been reported that to construct a single page in Amazon's retail platform requires to invoke more than 150 different services. That means individual services may only get a budget of like 10 milliseconds for both computation and communication. As a result, for network communication in the cloud, it's not only that the average latency must be low, the tail latency matters. For a system with large fanouts, even if a single service gets slow, your entire transaction may miss the deadline. While the tail latency is very critical, in this talk, I'll show you that in Amazon's EC2, which uses virtualization to manage the hardware, suffers from a long tail latency problem. And that problem is much worse than that in dedicated data centers, the ones like Microsoft and Facebook use. Intuition tells us that the primary cause in those dedicated data centers for the long tail latency is network congestion. And the talk given by the first speaker in this session again confirmed that intuition. However, in this talk, I'll show you that in Amazon's EC2, for the problem we studied, it actually is a property of nodes, not a network. Then I'll use controlled experiments to convince you that the root cause of the problem is actually the co-scheduling of incompatible workloads on shared hardware. Knowing the root cause, I'll present to you Bobtail, our solution to the problem that help developers avoid those VMs that suffer from long-tail latency and without any help from the service providers. Now let me start with a demonstration of the long-tail problem in EC2, use our large-scale measurements. And here's how we did it. All our experiments are did in EC2's east region. Instead of using raw socket measurement, in our experiments, we use a RPC framework called Thrift, thanks Facebook, to measure the amount of time it takes the RPC client to get an answer from the RPC server. We believe that will give us a better understanding of application-level performance. In this talk, I'll present you two experiments here. In the first experiment, we used designated nodes to test the round-trip time against 60 servers in the same data center, and the aggregated result and give you the overview of the problem. Then, we studied the spatial properties of the problem by launching another 16 servers and let them do pairwise RTT measurement against each other. Now let me show you the result. In this figure, we showed the tail part of the latency distribution that aggregated the result for 60 servers. So the y-axis starts from the 99th percentile, and the x-axis is in log scale. The first question is, of course, how bad is the latency tail in EC2? Our measurements showed that at 99.9th percentile, it is close to 30 milliseconds. If we compare that to the median latency, the difference is over an order of magnitude. Now, the next question is, how bad is that compared to dedicated data centers? So we quote the numbers from recent studies, which show that our result is at least twice as large as that numbers we quote for dedicated data centers. And in fact, we've seen individual cases where there are examples that are up to 4 times as large. So we know that both virtualization used by EC2 and the measurement framework we use both add overhead to the latency, but we did not expect the difference to be this large. So next, let's look at the results for the spatial experiments and see if that gave us any clues. So recall that we started spatial experiments by launching 16 instances and let them do pairwise measurement. So this heat map summarizes the result. Here, each column, each row here represents the client of RPC core, and each column represents the server. The color here indicates the latency at 99.9 percentile in milliseconds. So because the round trip time measurement we took is by definition a symmetric measurement, so when we start the experiment, we expected to see a heat map that is actually symmetric across its diagonal for each pair of client and server. However, that expectation didn't come true. Instead, we see those vertical bands here that have very different colors. These unexpected observations tell us two things. First of all, the asymmetry means the problem we study here is actually a property of nodes, not a network. And the tail latency only depends on, or mostly depends on, the servers, and the clients have very limited impact. So at this point, we've learned that EC2 has a long latency problem that is much worse than that in dedicated data centers. And that problem is a property of node, not a network. Next, I'll use controlled experiments to convince you that the root cause of this problem is the co-scheduling of incompatible workloads on shared hardware. And here's how we do it. First of all, it has been shown that virtualization and processor sharing cause high variance in EC2 network performance. So in other words, if no sharing, no tail. But we go a step further and ask the question, does the type of sharing matter, and why? To answer these questions, we conduct controlled experiments on our local testbed, for which we use a recent release of Zen for virtualization. In these experiments, we run 5 VMs on 2 shared processors, so each get 40% share. And on these 5 VMs, we vary the workload combinations in these 5 VMs with 2 generic workloads. And one is CPU bound, which we keep it busy 85% of the time. And the other is I/O bound, which is essentially the same thing we use for the measurement. And now let's see the result. At the beginning, we let all 5 VMs run only I/O bound workloads in each VM, respectively. And I show the latency distribution as before for one of these VMs. As we can see here, even at 99.8 percentile, we don't see very large latency. It's way below 1 millisecond. So in other words, 5 VM, all I/O-bound workloads, no impact. If we replace one of these I/O-bound VM with a CPU-bound VM, the result is almost identical, so no impact. But if we do it again with just a second CPU-bound VM, then the tail latency is all of a sudden increased by more than an order of magnitude. As you can imagine, if we keep doing that, in the end, when we have 4 CPU-bound VMs and just 1 I/O-bound, the latency we see is almost as bad as we have measured in EC2, but here on our local testbed, there's no network congestion. What we have learned from these experiments is that the type of sharing does matter. The root cause is the co-scheduling of incompatible workloads on a shared platform. However, sharing is not always bad, because in our experiment, the long tail only appears when the total number of CPU-bound VMs is at least as many as the number of available CPU cores. In other words, sharing with only I/O-bound VMs is fine. This is a very important observation, and later we'll use that to construct our solution. But before we do that, let me explain why the type of sharing matters. So imagine in our experiment, we have 2 CPU cores. If we have 2 or more CPU-bound workloads running on them, then there could be a scenario where when a request comes to an I/O-bound VM, both CPU cores are occupied by 2 CPU-bound workloads. Then the underlying VM scheduler may decide that at this moment, I don't want to preempt those CPU VMs to let I/O-bound VM to process the interrupts. As a result, that particular request will experience very large latency. However, this scenario doesn't happen very often, so the average or median latency is not affected. However, it happens often enough so that the tail latency is affected. Now, the next question is, why 30 milliseconds for both measurement and control experiments? It turns out that the VM scheduler we use by default uses a 30 millisecond time slice. In other words, a VM cannot run for more than 30 milliseconds without being preempted. In fact, in the most recent release of Zen, we can tweak that value, which means we can bring down directly the tail latency that we observe by decrease that time size value. However, this is not free, because when you do that, you also bring down the throughput for CPU-bound workload. So there's an inherent trade-off between throughput and latency. We have a follow-up work to show you that, in fact, in the environment like EC2, where VMs and hardware are shared by different people from different organizations, it is very hard to come up with a scheduling policy that makes everyone happy. Now, finally, remember that in a heat map, the tail latency only depends on the server, and here's why. Because when a client sends out a request, its timer started when the client is already scheduled by the VM scheduler. But when that request comes to the server may have to wait to be scheduled before the interrupt can be processed. That's why when bad things happens, it mostly depends on the server side. Now, we know EC2 has a long tail latency problem, and we know what the root cause is. Now let me present you Bobtail, a solution that helps developers to pick VMs that don't suffer from the problem without any help from the service providers. Remember, the key insight we have is that it is the CPU-bound VMs that delayed interrupt processing of its neighbors. In fact, that happens to any interrupt, not just network I/O. So what we can do is actually use a local testing program to determine whether or not that VM suffer from a long latency problem by measuring whether the interrupt processing is delayed. And here in our experiment, we use timer interrupt because it's easy to manipulate. Now, here's how Bobtail works. Say if a customer needs to run n good instances for their latency-sensitive workloads, we can actually pick k times as many as candidates. This is just one-time cost because we pay EC2 by the hour. And then, in each of these candidates, we run simple testing program that sleeps periodically, say every 100 microseconds. And then when it wakes up, we see if we overslept, which means the timer interrupt is delayed by the neighbors because of incompatible sharing. Then we can pick those VMs that rarely oversleep to run latency-sensitive jobs, and for the rest, you can keep them for other purposes or just kill them. Now, this approach works very well on our local testbed. Let's see how it works in EC2. So we run the evaluation in 2 of the EC2 data centers in the east region, and we use Bobtail to pick 40 instances out of 160 candidates. Then we compare that to the baseline, which we use EC2's API to launch instances directly. Among all the benchmarks we used, in this talk, I'll just present you one simple example. This is actually the worst result for Bobtail. And here's how it works. It's called partition aggregation. So as you imagine, in each transaction, the client sends requests to all servers in parallel and wait for all of them to come back. So it is the slowest one that determines the delay for the entire transaction. Now here is the result. We have 6 figures here. Each column represents a different data center, and each row represents a different number of servers involved in a transaction. In each figure, the x-axis represents the different transaction rate, and the y-axis is a percentage improvement over the baseline. So, and the bars in each figure represent 99 and 99.9 percentile results respectively. So as we can see, these 2 data centers have very similar results. So let's just look at one of them. So at the beginning, we see considerable improvement over the baseline, just as in other benchmarks. However, as we add more servers to the transaction, the benefits of using Bobtail diminishes. However, this is not because Bobtail becomes useless with larger number of servers. Instead, this is because when we use Bobtail to solve the problem we described in this talk, other latency problems, like the network congestion that we are familiar with, become non-negligible. In other words, these other latency problems have a smaller impact than the one we study here. So they're buried in the distribution before we apply Bobtail. Once Bobtail is applied, these other problems become non-negligible. So naturally, we have our next paper to tackle these other problems. Before I wrap up, I want to share two other thoughts with you guys. The first one is, people may ask, what if everyone uses Bobtail? What would happen? We have to note that here that Bobtail is not exclusively looking for empty spaces where there's no sharing, because no sharing, no tail, but we don't just look for those spaces. Instead, we also seek to share with other compatible workloads. So one possible scenario that could happen if everyone uses Bobtail is that at the end of the day, the entire cloud data center will be self-partitioned, where in one partition, most of the workloads are I/O bound, so they don't cause long tail to each other. And the other partition, most of the workloads are CPU bound. And it turns out that this partitioning scheme is actually also beneficial to CPU-bound workloads, because in that scenario, these workloads would experience less context switch and high efficiency in CPU cache usage. The other thought is, Bobtail here offers a solution above the virtualization layer that let developers to solve the problem by themselves. Alternatively, we can imagine Amazon can fix this problem for us by attacking directly the layers below the virtualization or guest VM. There are a few alternatives we can do that, and each of them have their own trade-offs. We have a follow-up work for that, so I'm not going to go through the whole list here. The argument we're trying to make here is that there may be other performance-related problems that you can find in EC2. So from a developer's perspective, you can either wait for providers to fix all these problems for you, or you can try to understand them and deal with them. Both approaches are complementary to each other. So to sum up, we find this long-tail problem in EC2 by using both large-scale measurements and controlled experiments. We reveal the root cause of the problem to be the co-scheduling of incompatible workloads, and we presented Bobtail that help developers avoid the problem without any help from the cloud providers. Thank you for listening to my talk, and thanks our sponsors. I'm happy to take questions.
Hyuntaek Lim from Carnegie Mellon University. Mm-hmm. So what happens when a VM contains both IO-intensive and CPU-intensive processes?
You mean when a single VM contains both types of workloads?
Right.
In that case, there are two perspectives here, right? There's the neighbors, what neighbor sees, and what yourself sees, right? So for that particular VM, what you can see is your own latency-bound application would suffer long tail because you have bad neighbors in your own VM, right? And for your neighbors, for other VMs on the same physical machine, what will happen is it will appear as if your neighbor is just CPU-bound, because that would dominate how the scheduler works for all these VMs on the same physical machine.
Okay.
Günser, Cornell University. So I liked the sort of the lessons you drew from the data you gathered, but there is a completely different way to look at the entire problem.
Okay.
And if you could go to your first graph, I'd like to maybe share it with you.
Okay.
So
let me see if I can go there. Okay, this one?
No. Yep, that one. That's good. So you seem really concerned about the longness of the tail.
Yes.
And you seem also very concerned about the height at which it appears.
Yes.
I posit to you that neither matter, that the only thing that matters is the steepness of the knee. And if you were to have a very sharp rise followed by a sudden turn, it doesn't matter how deep that line goes. It could go to 30 seconds if it wanted to. What you would do is you would issue the request, As soon as you waited long enough to go past that curve in the knee, you'd say, okay, screw this. This was a bad server to have issued the request to. You would issue it to another server. So it's quite easy to solve this problem as long as that curve has that shape.
I agree with you, but I would add just one comment. If the curve is not as deep, then it is an easier problem to solve. I agree. But you still have a problem as long as you have a large value at a certain point where you care. Say, let's see here, the 99 percentile at the bottom is actually pretty good. It's just a little bit larger than 1 millisecond, right? In other words, if your application only care about 99, then I say there's no problem here, right? If you do care about 99.9 percentile, then this is a problem you have to worry about.
No, you would issue it, and then you would cut off at the 2 millisecond level, and you'd issue it to somewhere else for an average expectation of, I can't do the math in my head, but you'd end up getting something like on the order of 4 or 5 milliseconds for your cases.
Okay, I see. I think we should take this problem offline. Yep.
Hi, I'm Chang Kim at Windows Azure. So, interesting talk, but I mean, suppose you don't have any CPU core over subscription, and then suppose you use a recent NIC technology that allows you to bound incoming packets directly to particular VMs based on the VM's unique identifier, such as MAC address. Wouldn't you be able to solve this problem in the first place?
Yes. So actually, in our last slides, last second, this one we showed that if you can reduce the VM density per core, say if you only run 1 VM per core, it effectively means there's no sharing on any core, right? You share hardware, but you don't share any core, then there's no problem.
No, because the incoming if incoming packets can interrupt any CPU core, you still have the problem.
Usually, so there can be many different type of deployment, but in EC2 scenario, what we learned is, not in EC2, but if you use Xen, usually what happens, you allocate cores for the host machine or the domain 0 to process I/O exclusively. And then they will set virtual interrupt to the VMs who will actually need those packets. That's the current deployment model. So I don't know if that answers your question.
I just wanted to say that some other recent NIC technologies give you to avoid that problem.
Yeah, so I think what you're saying is if you have one CPU per core, one CPU per VM, and you have multiple virtual NICs that can be assigned one per VM, then there's no problem. Then if that is the case, I agree with you.
Hi, Feng Lu from UCSD. Very interesting talk. So you have some way of inferring whether your VM is co-scheduled with a CPU-intensive VMs. I'm just curious, have you ever looked at, say, that some way you are able to find a ground truth to validate your findings?
So I think the best we can do here is to mimic what we can learn from the EC2 configuration and did our control experiments, and then go back to EC2 and see if the speculation we make for our solution actually works. But we don't have any ground truth from inside of EC2.
Got you. Thanks.